Okay, so we are now going to solve that time-independent Schrödinger's equation. So this is the time-independent Schrödinger's equation, right? Which, remember what this Hamiltonian operator is? We have the second order derivative and the potential. So this is what we saw, the time-independent Schrödinger's equation. Okay, and we are now going to solve it. And to solve it, we need a potential. So we are going to be solving our first potential, which is known as infinite square well. So this is the first case that we'll be solving in this chapter 2. This is the beginning then of this section 2.2 in Griffiths' book. So what is this? What is this infinite square well? Well, I'm going to write it here. Is this potential energy of X written like that? It's zero in a certain interval where between X 0 and X a certain value, a certain position A. And it's infinite otherwise. Well, what does it mean? Well, let's try to make a graph for this potential. If I would draw that, it would be something. So if I want to draw my potential, it would be something like this. Right at 0 and any place for X smaller than 0, there is an infinite wall here. Right at A and above A, there is an infinite wall. Okay, so the particle can never be in these regions because there is a barrier, an infinite barrier there. So the particle can only be found somewhere inside, okay? Somewhere inside this well, this infinite square well, okay? So for this potential, we are now going to write our time-independent Schrödinger's equation. Okay, so let's start. Minus h squared over 2m, the derivative, the second order derivative, and now comes the potential. Well, the only region where the particle can be found is the region inside the well, where the potential is 0. Okay, so I'm not going to write this part. My potential is 0. The only thing that we'll have is the right side. Okay, all right, now that's the equation that we have to solve to be able then to solve the time-independent Schrödinger's equation. So what does it mean to solve this Schrödinger's equation? It means to find all the energies and the corresponding states, the corresponding functions of X. Okay, now remember what we said. There is not just one energy. There are many, E1, E2, E3, and so on. And the corresponding functions. Okay, so this is what we have to do. We have to find this set of solutions for this time-independent Schrödinger's equation in the case of the infinite square well. Okay, so let me rewrite this equation in another form. Let me keep on the left side only the second order derivative. And on the right side, I'll put everything else. So there will be minus 2m divided by h bar squared energy and psi. Okay, and just to simplify our lives, instead of keeping writing the m for mass, the h bar, the energy, let me use this whole thing. Let me substitute this whole thing, this whole constant, with a certain symbol. Okay, it could be A, B, whatever you want. Well, we are going to be using k, okay? But k squared, you might say, why k squared? Well, because of the way that this equation will look. It will be, the equation will now be written like, so it's convenient to have that k squared. Because this is, you look at this equation, then you probably already know the solution. And so the question here is, what is the function that I derive it once, and then I derive it twice? And what do I get? I get back the function. I get back the function with something in front of it, which is a negative k squared. Okay, so the question is now, what is this function? What is the solution? And you probably know already. What are the possibilities? It could be, for example, sine of kx, correct? If I derive it twice, I will get back my function with that minus k squared in front of it, correct? If I do the first derivative, I get k and then cosine of kx. If I do the second derivative, well, I'll get another k, so that's the k squared. Because it's a cosine, I get the minus, so I recover minus k squared sine of kx. Okay, so this is an option. What is the another possibility? It could be cosine of kx, correct? If I do the first derivative, I get minus k and sine of kx. And then the second derivative minus k again, k squared, and back to the cosine. So this is the solution for this equation. As you might know, a sine or a cosine, and then you may wonder which one am I going to use? Well, we are going to use a linear combination of both, because if sine is a solution, if cosine is a solution, the linear combination, this is big A is a constant, the linear combination between this sine with the cosine will also be a solution of that equation. So that's it. We found it. So we found the function that is solution of this equation. All right, great. But there are some issues. No? We don't know what this big A is. We don't know what the big B is. And we don't know K. And K is really what we want. Why? Because remember how we define this K? This K is related to the energy, and energy is what we want. So we are after that K. No? So we'll be able to find our energies. We already got the form of this function, but with some unknowns, the A, the B, and the K. Okay, so how are we going to proceed from now? We are going to use now what is known as boundary conditions. What does that mean? We said that we have that potential where from 0 and below, the particle cannot be found. So if the particle cannot be found from 0 to below, well, we have a wave function, we have this function describing the particle inside this well, but whatever the function is, whatever shape it has to become 0 at this point, because beyond this point, the particle cannot be found. Okay, so this is one of the boundary conditions. The function at 0 has to become 0, okay? There should be no probability to find the particle at this point 0 or any value below 0. And for the same reason, we have another wall here, right? So whatever happens to this function, when it reaches this point A, it has to become 0, okay? No probability to find the particle there or beyond. Okay, so these are the boundary conditions, and we are going to use these boundary conditions to try to find these unknowns that we have in the shape, in the way that we wrote the wave function, in the way that we wrote the function. Okay, so let's start with this one here. at x0, the function at 0 is a sine of k, now x is 0, plus b cosine of k, and x is 0. Well, this is sine of k0, this is sine of 0 is 0, so this disappears. Cosine of k0 is cosine of 0, which is 1. So that means that we got at that position 0, just b. And the boundary condition here tells us that this is 0, therefore b is 0. So we had all this trouble to write the solution in this nice form, and we just discovered that this part does not exist. Okay, that's a simplification. Let's now check the other boundary condition, which is this one. Okay, so again, let's rewrite the function at point A, and now we already know that cosine does not exist. The only thing that survives here is big A sine of k little a. And what the boundary condition tells us that this thing has to be 0. All right, so let's isolate what we just found. What we just found is that at A, this is 0, and because of that, big A sine k little a has to be 0. Okay, so what does it tell us? What are the possibilities? How can we guarantee that we will have this 0? You could say, well, I'm going to make this big A 0. That would be a bad choice because then you kill the whole solution. You killed your function. Huh? So not this one. We could say, okay, so then let me work with this sign. I know that sine is 0 at some scenarios. For example, if this thing is 0, okay, that's good. But again, if you use that solution, you'll be killing the sign. So you kill the function. What are the other possibilities to have this sign equal to 0? Look at that. How about pi? Or 2 pi? Or 3 pi? And we can continue with any multiple of pi. So why not 0 here? Because this would imply that k is 0. And if you put k 0, remember the function is this. If I put k 0, I will be killing the whole function. But if I put k pi over a or 2 pi over a, I'm not going to be killing the function. Let me give, for example, this possibility. I'm not going to be killing the function when x is not a. Yeah? So did you understand? So that's why I'm not going to consider this case, just as I didn't consider this case, because I killed the function at any position x. So that's not good. I want to kill the function only at x equal to a. Okay, so that's why we are not considering these two cases, but there are many cases that we can consider that will guarantee that the sign of k a is 0, but not the sign of kx, only when x is equal to 0, or only when x is equal to a. Okay, so let's come back. If this is now clear, let's come back to these possibilities. The other case that you might say is, okay, how about then minus pi or minus 2 pi? They are also possibilities. You're right. But then, look, if I have a function, this should be the sign. Huh? So if I have a function like this, where inside I put a minus, I know that I can write this as this function, yeah? But we don't know yet what this A is. So I can incorporate into this A, this minus, and call it another A. And so we don't need to take into account the negative minus pi, minus 2 pi. We are only going to take into account the positives, positive values, okay? So all that to finally conclude. K, A will have to be a multiple of pi. So I'm going to put here n. This n can be 1, 2, 3, any value that you want, any natural number that you want, except 0. Right, so if it can be any n, let me put an index in this k, the index n. So, and what have we just found? This is a very important result. Remember what k was? Let's go up there. We said that k is related to the energy, right? K squared is related to the energy. Let's write this down. We wrote in the beginning, that's how we defined that k squared was equal to 2 mass of the particle energy divided by h bar squared. And we have now just found a relationship for this case. So let's combine the things because this will finally give us the energy, right? So let me square this, this equation. I have k squared, a squared equal to n squared, pi squared. Okay, so I'm going to write this now as n squared, pi squared divided by a squared. And I'm going to put what k squared is. So now I have 2me divided by h bar squared equals to n squared, pi squared, a squared. All right, so we finally found an expression for the energy. Let's rewrite it. Isolating energy here, we have n squared, pi squared, h bar squared divided by 2ma squared. Now, for the same reason that I put this index here for the k, I'm going to put this index here for the energy. This is the solution. We found the energies for this scenario of the infinite square well. So we found the E1, we just need to put N1. We found the E2, we found the E3, and so on. Okay? Look what we conclude with this result, and this is very important. Let's see what we've seen so far. This is a very important concept of quantum mechanics, what we are seeing in this equation. Well, look, we discussed in previous classes that in quantum mechanics, the way the particle is described, we know information about the particle through the wave function. So we have now a wave describing how this describing the system instead of the exact position of the particle as we do in classical mechanics. We deal with its wave. Okay, so this was an important concept, the story of the wave function. Another thing that we discussed, which is another important concept in quantum mechanics, is that we can never know the position and the momentum at the same time with absolute precision. There is always an uncertainty associated with them. That was the uncertainty principle. What have we just found now with this equation? We just found that energy is discrete. Okay? Energy is discrete. It doesn't have any possible value. Yeah? It comes the only possible values is when n is 1, when n is 2. We don't have anything in between. The same, you already knew about the discreteness of the energy. Now, if you would think, for example, the hydrogen atom, which is the simple atom that you've heard and learned before. You have these many levels. We can talk about the energy E1, the energy E2, but we are not going to find a level in between. Okay, so it's the same story of what we are seeing here. Now, this equation is telling us that I have E1, I have E2, but I don't have any possible value in between. Okay, so energy is discrete. Very good. Okay, so we found our energies, and I'm going to write it here again. These discrete energies for the solution of Schrödinger time-independent Schrödinger's equation for the infinite square well. So these are our solutions. Okay, now for each energy, we have a corresponding wave, a corresponding function. And what is that? Well, we already made a lot of progress. We said that this function has only the sign part. This sign is of kx. Very good. We already found k. What is missing? The big A. So we don't have any other boundary condition. We already used what we had. What remains? What else can we use to find this A? And the answer now is going to be normalization. Okay. By normalizing that wave function, by guaranteeing that this is equal to 1, I will be able to find the A. Okay, so how we were doing this before, we were going from minus infinity to infinity. But remember, in this problem, the particle can only exist from 0 to A. So that's the integral that we have to solve. So let's go. We have here the A, so I'm going to put absolute value square, not just A square. So I'm being very careful here because in principle, this A could be a complex number. The wave function can be complex. And what else do we have? Sine square of kx from 0 to A. This is what we have to solve. Let me put this A outside the integral because it's a constant. And what we have to solve is this sine square. All right. How do we solve sine square? Well, integral of sine square. So it's very important in this course to know about all these trigonometric relations because you'll be needing them. You'll be using them a lot. So let me review with you some of these trigonometric relations. Well, for example, cosine square plus sine square, you know it's 1. Cosine of 2x is cosine square minus sine square. Sine of 2x is 2 cosine x sine square, sine x. So if you don't remember these things, try to remember, go back to the course that you had on trigonometry to remember these relationships. They will be needed, okay? What else do you know? Cosine of x is e exponential of ix plus minus ix divided by 2. Sine is, oh no, don't have space. Sine, where I'm going to put the signs. Sine of x, ix minus ix divided by 2i. Yeah, so try to remember these relations. They will be very useful and already to solve this integral. How are we going to solve the integral of sine square? We know the integral of sine, we know the integral of cosine, but how about sine square? So let's try to write the sine square in terms of a cosine or a sine. Let's try to get rid of that sine square or that square. Okay, so how can we do that? Well, let's go back to our trigonometric relations and let's play with these two. How? Well, let's write, and I'm going to add now the k because there is a k in this story. Okay, so let me look at the cosine of 2kx. According to this relation here, cosine of 2kx is cosine square of 2kx. Oh, sorry. Cosine square of kx minus sine square of kx. Okay, good. So this is what we have there. All right, good. And I see here a cosine showing up. So that's nice because integral of the cosine I know. But the annoying thing is that I will still have this cosine square. Well, but I can get rid of this cosine square through this relation here. So what is this cosine square? I can write that as 1 minus sine square of kx. So then we have that the cosine of 2kx can also be written as 1 minus 2 sine square of kx. So that sine square of kx that we have in our integral can be written as 1 minus cosine of 2kx divided by 2. That's what we are going to use to solve that integral. Okay, so let me come back. We have to solve this. Sine square. Well, let me get rid of that square and write it using this relation. So now I have two integrals. One of the half and that other integral. And both going from 0 to a, 0 to a. Okay, so you see now we can solve because it's a cosine and integral of a cosine we know. So we have from the first integral, we just have a over 2 because the 0 is 0. From the second integral, there is a half there. And now the integral of the cosine of 2kx will give us sine of 2kx divided by 2k between the integral there, the extremes between 0 and a. All right, now what do we know? Sine of 2ka, or we know that at that point a, this has to be 0. And the other one, sine of 2k0, of course, is 0. So you see, this does not exist. And then we found that, remember what this was, right? This thing is the normalization procedure. We were trying to solve this part, and we wanted to guarantee that this was equal to 1. And so that means this is equal to 1. So we find that that big A is the square root of 2 divided by a. Perfect. So now we have our wave function. So let me write everything that we got. We have the energy with this index n, where n is 1, 2, 3, 4 discrete energy. So we have this energy, n square, pi square, h bar square, divided by 2ma square. And what is the corresponding function? What is the corresponding function is that psi of x. Now, instead of big A, I'm going to put what we just found. Square root of this ratio. And then here we have the sine of what? Of kx. Now, just as here we have this index, here I'm going to put an index as well. Okay, so that means we found what we wanted. E1, when I put n equal to 1, we have E1 with the corresponding function psi1. And for E2, we have the corresponding psi2, and so on. Now, so these are the solutions for the time-independent Schrödinger's equation when we are dealing with the infinite square well. And this is a very important result we'll be using over and over again in this course. Okay, so this is the end